Hey everyone. This is another assessed quiz feedback presentation. This time we're going to be doing quiz 2 and we're going to be focusing on one question in particular. This particular question was not answered so well in general, as in almost half of all the students didn't answer it correctly. So it's well worth having another look at. So that you know what we're talking about, this is the question that we're going to be looking at today. So before you continue, I want you to pause the video, read the question, picture the scenario in your mind, think about how you would answer it, get it all into your working memory so it's ready for us to access as we pick it apart in the next few slides. Okay, so let's break it down. The first sentence just tells us what the scenario is. We're screening for a disease. The rest of the paragraph gives us some information we can actually use in our calculations or to work out the probability of having a disease or not having a disease given whatever evidence we might collect. So those numerical bits of information are first the accuracy of the test. Now, accuracy is the same as likelihood or reliability. In earlier weeks, likelihood was mentioned a few times, and reliability was used by Andrew in week 8. Now, every time we've referred to this concept, we've described what it means, and we've linked it to the mathematical symbols and that make up the component of Bayes' equation. So the confusion in those terms might have tripped a few people up, but hopefully not too many, because it is described in English what accuracy means and what it means to be 95% accurate. All right. Well, the second piece of information we're given in the last sentence is the overall prevalence of the disease. Now, similar to accuracy, the meaning of the word prevalence can also be referred to by another term, which is base rate, and we've used that a lot of times throughout the semester. If you didn't know the meaning of the word prevalence, I'd encourage you, well, it's a bit late now, but next time in an open book test, grab hold of a dictionary, or just Google what does prevalence mean. Hopefully most of you thought of that if you didn't know what prevalence meant, but if that didn't occur to you, I guess that's why we're here. We're learning for next time. So the next step, now we've got these two bits of information, is to use them to answer the question, or even before we do that, to help us understand the situation a bit better. So we can think about how we can use this information to understand the situation. One way to do that is to link it to components of Bayes' equation, and given that we know what that equation is, we can do some maths, or we can go for a more diagrammatic approach, like a tree diagram. And tree diagrams are what we will start with. So here we're going to look at two tree diagrams and work out which one of them has a place for our accuracy statistic. So the first one is on the left and the second one is on the right. Now, which one allows for us to describe accuracy? You'll see down the bottom, we've got 95% and 5%, and then the same on the other one. Which one makes sense? Now pause the video, have a think about it. All right, now that you've had a think about it, you've unpaused the video, I will tell you that the one on the right makes sense. Now, if it's hard to understand why, The one on the right is correct. You need to have a close look at the wording of the description of what accuracy is. It means that if you're sick, let me get a pen. If you're sick, there is a 95% chance that you will test positive. Not like it is on the left-hand side. It's not a 95% chance of you being sick if you're positive. No, it's not that. And hopefully you guys can see how this links to the components of Bayes' equation. The first level down on the right-hand side is our hypothesis. Assuming our hypothesis 1 would be that we're sick, hypothesis 2 would be that we're well, and the evidence that we're collecting is a positive or negative test. And this is the bit that will hopefully help it make sense. The second level down is a conditional situation. It's the evidence, or on the right-hand side, the last level is the evidence given the hypothesis. So it's come from the hypothesis. We're going down. And for these two leaves, they've sprung from the well node. So this let's say this positive would be this situation. The set here would be those who have tested positive given they are well. Now, in this situation, the set would also be those who are well and tested positive, but if you're wondering what's the difference between the two, the answer is it doesn't matter here. So we've got our correct tree diagram. What do we do with it now? How do we answer the question? Well, let's use natural frequencies. So what we'll do is we'll work out how many people would be in each node down here at the bottom. So we'll call this node 1, node 2, node 3, node 4. And let's say if we started with 10,000 people, what would the numbers be down the bottom? So we've got 1 and 9,999. Now, if you're wondering where these two numbers come from, they come from the base rate. And remember, the base rate was that 1 in 10,000 people are sick. So if we start with 10,000, 1 will be sick and will be in this node. And then the rest of that 10,000 will be here. Cool, now we've got groups of sick and well, and now it's time to apply the accuracy as described before. So 95% of the sick people will test positive, 95% of the well people will test negative. And here are the calculations. Just getting a highlighter. So each line is an equation for the number of people in each node. It might seem strange to you that there is 0.95 people in node 1. If that bothers you, just multiply everything by 100 and pretend there's 95 people, and pretend that we started with a million people instead of 10,000. So if there are 1 million people to start with, there'd be 95 down here. And there'd be 50 in number 2. And nearly, yeah, you can read the answers. So now that we've got the numbers of people, let's work out the probabilities of our, there we go. These are the equations to work out the probabilities of that we need to answer the question. So the probability that someone is sick given they tested positive is the number of people who are sick given they tested positive divided by the total number of people who tested positive, which is node 1 plus node 3. And then this bottom one is just the accuracy. Again, if you're not sure why, go look at the wording of the question and you'll see that that is what the question describes accuracy to be. And now we can obviously see that this one is smaller than this one. And hopefully that'll help you answer the question. Now, if you have, it's also possible to answer this question without drawing a T-diagram and doing the maths, but you have to have a really good sense of the numbers or how it works, how significant the base rate is, because the thing that allows you to do that is that 1 out of 10,000 is very, very small, and it's sort of overpowers the accuracy of the test. Doesn't mean the test is useless, because if we get a positive test, we become a little bit more confident in the likelihood of someone being sick. The probability of someone being sick without doing a test, all that we know is that it's 1 in 10,000. If we get a positive test, the number increases from 1 in 10,000 to this number here, which is slightly bigger. It's still more likely that you're not sick, but I don't know, I guess you do another better, more expensive test. Hopefully that makes sense to everyone.